Hi, welcome. I'm glad you all are here. This is my fourth FOSS4G and my first time presenting. My name is Mark Isley. I'm a data manager and physical scientist with the Chihuahuan Desert Network. That's a Park Service unit as part of the Natural Resource Stewardship and Sciences Inventory and Monitoring Division. That's a mouthful. We are responsible for monitoring the natural resources of the Chihuahuan in the parts of the Chihuahuan Desert. That's in western Texas and southeast New Mexico. Today I'm going to tell you a little bit about White Sands National Park and how things I learned at FOSS4G in North America in 2019 in San Diego, as well as tons of posts online from the community have led to advances in our ability to monitor environmental conditions at White Sands. The title of this presentation is about open science in NPS. As part of the open science efforts throughout the federal government, we're striving to make as much of our science open as we can. Throughout the Inventory and Monitoring Division, we're working towards making as much of our data available as possible as open data. Feel free to ask me more about that afterwards. In this presentation, I'll be focusing on using open data from Landsat and open tools that I learned about originally through the Pangeo project and its contributors. Messiest slide, I think. This story starts with the FOSS4G community at the FOSS4G North America in 2019 in San Diego, where I was able to attend two talks that were given. The first was a talk about stack services, how to query stack services, that I think was given by Matthew Hansen from Element 84. The other was a talk given by Scott Henderson, which explained the Pangeo project and how the Python packages they were contributing to could be used to access imagery. As I started digging around, I found the community extended into the Department of the Interior as well. Ridge Signal at USGS had examples of how to set up and run Pangeo environments on resources that I had access to. This included the HPC cluster tallgrass in the middle on the far right there. In February of this year, I got access to Microsoft's planetary computer, which allowed, among other things, is based on these tools as well. Most of the rest of these examples will be based on work that I've done in that environment. In order to understand our monitoring efforts, we need to understand a little bit about the characteristics of White Sands. White Sands is the largest gypsum dune field in the world. It's located in the Tularosa Basin in south central New Mexico between the San Andreas and Sacramento Mountains. Its origins are rooted in the geologic evolution from the shallow Permian Sea 250 million years ago, which supplied the materials to make the gypsum, to the ancient Lake Otero, during the last ice age occupied about 1,600 square miles of the Tularosa Basin. As the climate warmed, Lake Otero dried up, and about 10,000 years ago, and a process of gypsum crystal formation and wind-driven erosion began, which continues today. Gypsum crystals form from flooding and evaporation in the remnant Lake Lucero in the southwest corner of the park. From there, they're transported by the prevailing southwest winds towards the east, where they stack up and form the dunes. What makes White Sands so uniquely large is a lens of water that's suspended above the clay cirrus of the ancient lake, between the dunes, 30 to 120 centimeters below the surface. The gypsum is saturated with water. This suspended shallow water aquifer holds the sand in place, providing resistance against the blowing wind. So, other than an interesting and unique geologic phenomenon, what makes White Sands so important? Well, you might have heard about White Sands in the news lately due to recent discoveries associated with human habitation of North America. Has anybody heard about that? All right. These discoveries from were human footprints fossilized in the sediments of ancient Lake Otero. It's not just humans either. There are prints from giant ground sloths, woolly mammoths, dire wolves, and other things. What makes these fossilized trackways so significant is that seeds and pollen and other evidence point to humans being in North America 21 to 23,000 years ago, well before previously accepted. So there's a huge cultural and anthropological significance to this landscape as well. One of the major factors affecting white sands are large dust storms, where large amounts of gypsum sediment are transported out of the dune field by wind. These events happen when climate conditions cause soil moisture levels to drop, and high winds, often in the springtime, blow the gypsum sand out to the east. In the image in the middle of the screen here was taken by astronauts on the space station in February 28th, 2012. There are several other events documented in daily MODIS imagery. These storms cause extensive erosion and impact visitor experience and park operations. They're also erode the fossil trackways and expose new layers of older tracks. So what are we doing to monitor changes? Well, my group's effort, which also includes monitoring groundwater and springs, soils and vegetation, and dune movement, have been focused on developing methods for assessing the stability and integrity of the dune field using remote sensing imagery. While there are several imagery data sets that offer a variety of additional benefits, what much of our work is used the Open Data Landsat archive due to its 40-year period of record. In this discussion, I'll focus on using two bands of imagery, the near IR, the near infrared, and the shortwave infrared, contrasted together with each other in a normalized difference water index. You can see an example of that on the right. The dune field is highlighted due to the high levels of soil moisture in comparison to the surrounding deserts. Our workflow is pretty simple, and you can find tons of examples out there online. We start with a querying stack. Is that real? Yeah. And we start with querying stack and a catalog and getting a list of images back with URLs that we can open. We open the catalog, specify a collection, in our case, Landsat ARD, then run the search with the area of interest, dates that we want to look at, and any specific properties that we want to filter by. In our case, we've identified 1,325 scenes from white sands from 1984 to 2022. When we filter those to just the complete scenes that covering the area and not the ones that partially cover the area, we end up with 1,278 images that make up our data set. As examples of how stacked metadata can be analyzed, the image on the bottom right shows how many scenes per month there are in our data set if we filter down to scenes with less than 25% cloud cover. The bottom left is a graph showing the number of days between scenes. It's kind of interesting how you can see big jumps when the satellites come online and go offline from the Landsat, 4, 5, and 7 dropping off and 8 coming back on. Before we start loading our analysis data, we need to create a couple of masks. On the left, we're creating we're using a simple function wrapped around raster.io's feature rasterization function to convert a GeoJSON area of interest, little bean shape, into an X-ray mask. On the right, we're accessing the QA pixel band for all the images and using a single lambda function at the very top, kind of hard to read, to figure out which of the over 10 billion pixels in the data set Landsat says are clouds, cloud shadow, or snow or ice. The output is a multi-dimensional array with 3 dimensions: the spatial dimensions, X and Y, as well as the time dimension, the temporal dimension time, holding the QA information for each scene. Now that we have our initial mask ready, we load in our analysis data and calculate our NDWI. On the left, we're using stack library to access just the near IR and shortwave infrared bands out of the whole band collection for Landsat. On the right, we're applying a mask, calculating the NDWI, rechunking the data into a computationally efficient structure. And that's a big piece of it. When you're in the back end of Dask, if you're below 100 megabytes or above 400 megabytes, you end up with computation issues. It slows things down. If you can see the times for these operations, they're very small, 227 milliseconds and 1.15 seconds. That's because we haven't actually done anything yet. The combination of cloud-optimized geotiffs and Dask delayed operations, which underlie X-arrays, data arrays, allow us to filter down the data from 1.62 terabytes to just over 37 gigabytes by only accessing the imagery's metadata. When we go to load the data into Dask, the compute cluster, into the Dask compute cluster, the operation takes about 3 minutes on Planetary Computer. Now that we have our data loaded, we need to make one more mask. In this case, in this step, we calculate the mean value for each pixel across the entire time series and use scikit-image to run edge detection and watershed segmentation to separate the dune field from the surrounding desert. You can see the result over there in the bottom left corner, or bottom right corner. With our segmentation mask applied, we can use a single simple line of code to calculate the mean pixel value for each year. Over on the left, the NDWI mean, their time.year, there's a time accessor in pandas, geopandas, X-array that allows really easy access to the components of a time index. We can use a long-term mean over the entire series from 1984 to 2002 that we 2022 that we calculated in the for the segmentation mask, and then subtract that from the annual mean, and that gives us what you see here in the top right. In this image, the pixels where the mean values for the year are above the long-term mean, they show up as blue, and the ones that are below the mean show up as red. You can see that there's variation over both space and time, and if we aggregate the spatial dimension, we can dimension of the annual differences into a single mean value. We can plot that time series, as you can see here on the bottom. In the image, the red lines are the times of known dust storms, and we can see that they occur during or after a period where the dune field has been below average, below the long-term average soil moisture. To look at within-year variation, we can do the same thing with monthly averages. We calculate the long-term average for each month and subtract that from the average for that month in a specific year. That allows us to see the variation in soil moisture within the dune field throughout the year. These images are from 2012, the same time as the image from the satellite, from the space station. And you can see in the bottom strip, the second panel, in the strip is February, and that's when the ISS image was taken. It shows a large amount of long-term mean values. It's kind of hard to see, but there's the whole the whole west side of the dune field is pretty much red there. And the following months, it continues to dry out. Here we've extracted the plots for February and March 2012, so you can see them in more detail. This is a snapshot of spatial variation within the dune field from 1990 to 2019. You can see variation within the dune field as well as variation over time. The trackways are in this area that keeps showing up most evidently in the red on the west side of the dune field. And so it's an area of lakes and playas. The bottom left corner there is the area is Lake Lucero. So places where you see the blue blips in the southwest corner, those are times when there's more moisture in Lake Lucero. And if there's been moisture in the dunefield in general and accumulated in Lake Lucero for a longer period of time, then you end up with the flooding and the gypsum crystal creation that keeps the dunefield going. And if we aggregate those spatial dimensions together we get a monthly time series. Red lines again are the dust storm. There's a lot of variation here. There's not, it's almost white noise. There is some periodicity to it. You can see that the dust storms almost always are connected with drier conditions, as we would expect. So our next steps that we're working on now are time series analysis. We took a feed both the pixel and the average time series into time series models and look for breakpoints in those. That's our next goal. We also have a real interest in finding out what's going on in these sub areas like Lucero or the active dunefield. There's a recharge zone on the east side of the park where a river called Lost River comes into the park. We're also hoping there's a lot of work been done with climate in the Park Service, and there's a data set available in NASA's APIRS platform called the NPS soil water balance data set, and we're hoping to work on tying these two data sets together, using the soil moisture for that one of the components of that data set. So bringing it back to open science, for several years now, we've been working with interns from the Scientist in Park program. This program connects us with emerging scientists and has specific focus on inclusivity. They ask job application questions about how the intern will support inclusiveness through their work. We hope to do more, such as make our analysis code available through public GitHub repos so that people can do their own analysis and make pull requests for what they come up with. So to summarize, these tools have given us the power to access large volumes of data and look at environmental conditions more continuously. They allow us to easily access information about both space and time. You have access to these data and tools too. What metrics are you going to calculate? If you have any thoughts, I'd love to hear them. A little early.